Hello everyone, welcome to Advent of Code in F# day 25. Merry Christmas. I hope you enjoyed your time yesterday. We're at the final day already. It's been a great year of puzzles, so let's see if we can end with a banger, with a last farewell and a great puzzle to end the year. Combo breaker. We finally reach our destination. Unfortunately, the registration systems are offline. Trusty old tech support. Room key is a small RFID card. Okay. We're on the 25th floor, of course. It takes what little energy we have left to climb the stairs. Of course, then our key does not work. Phone number for tech support. The card is not sending the right command. Okay. Reverse engineer the cryptographic handshake. Cool. I don't know the next thing about cryptographic handshakes actually. Handshakes used by the card and the door involves an operation that transforms the subject number. Subject number start with the value 1, then a number of times called the loop size. Perform the following steps. So we're transforming a subject number. We're squaring it. And 2020, 12, 27. We're modulo the 27th December for some reason. Okay, loop size is secret, so that's probably something we have to figure out. The door always uses a different secret loop size. The card transforms a subject number of 7 according to the card's secret loop size. Yeah, so we do the square it, modulus, square it, modulus for a secret number of loops. Then we have a public key. Oh, this is actually real cryptographic lingo. The door transforms the subject. So this is what the card does. Then the door does the same. Why are we talking about number 7? Okay. So yes, the loop size is the private key. No. It's a secret, the door and the card each have. Cool. They sign a number. That's their public keys, okay. The card and door use the wireless RFID signal to transmit the 2 public keys. Yeah. Now the card has the door's public key and the door has the card's public key. Because we can eavesdrop on the signal, we have both public keys, but we don't know the secret. Yeah. The card transforms the subject number of the door's public key according to the card's loop size. What? So the card transforms the subject number of the door's public key. So the card receives the door's public key, yeah, and it then tries to encrypt it again using its own secret. Then we have the encryption key. And these should both. So I should do this for card first, door next, and then door first, card next. They end up in the same encryption key. Is this actually how our RSA works? Flowchart, just what we need. Public key distribution, yes. Encryption, decryption, maybe. I don't know enough about RSA internals, but interesting. So cool. We calculate public keys. They exchange public keys, and then they both have the encryption key. And that's how they encrypt messages. If you can use the two public keys to determine each loop size, you will have enough to calculate the secret encryption key. So we need to figure out the encryption key. What's with this magical number 7? Where did it pop up first? That doesn't really matter. So, example. We need to figure out the encryption key, yeah? For example, suppose you know the card's public key is some number. With a little trial and error, you can work out that the card's loop size must be 8. Why? Okay, yeah. Because. Yeah. So, whatever we do, suppose we start with a 7 and loop for a certain number of times until we produce the public key. And we need to figure out what the number of iterations is. But we have a fixed seed, they both use 7, okay. I have the feeling that this will burn quite some computation if we do this naively. Yeah, we know the secret of one and have the public key of the other, we can build or reconstruct the encryption key. That makes sense. Okay. Select all the lines, thank you. Okay. Let's work on the example first. This is the card. Let's work with longs. Door. Okay, let's do the example first to see if we get the ID, and then just brute force it to see how far we get. A loop size of 8 and 7 is very reasonable. A loop size of whatever our input will need, that might be something else. So let's try the naive approach first. We know both the door and the card, the card and the door both have the same starting number 7. Right? No, they have a, yeah, they start with the same number and they have a secret loop size. So both start with something 7 and then they have a loop size which we need to figure out. And we figure this out by the secret, squaring it, and modulus magical number 27. What's magical about this number? Why is this number? Doesn't matter, it's just a number. So what is it called? So just keep squaring and modulus this. Okay, so Can you square like this in F#? I actually don't know. Float. Ah, interesting. Okay, then we'll do it differently. Okay, so it's actually not much of a problem here. It's one formula. So the problem will be in optimizing this or finding an optimal approach. So squared and module. Yeah. We had some examples, right? And now we need to figure out the how many loops the card and the door have to take, or just the one. Can we take the smallest number? Would it be the smallest number? Yes, squaring it makes it grow, and then we do modulus. I actually don't know. Is there a big difference in our number input? Not really. 9 million, actually it sounds not that bad. What? Yeah, let's try it. Let's try to take 7 loops. Or 8 loops, that's the smallest here. So yeah, let's try to take 8 loops. To figure out the card's secret, which is this number. So when they both start at shared secret. So let's write a function or a sequence that contains all the numbers. Yeah, that generates all the numbers because they share the same algorithm, they share the same secrets, so it's for both key and for both card and door, it's the same algorithm, so you can use this for both. So actually so it's this, and let's then just recurse. So, yeah. Oh, this is not really okay. We need to provide a number. So there we go. Let's call this. There we go. This does not have to be recursive. So let's take some of these numbers. 8 was it? Uh, 5764801. Why is this already a third? Is this reversed? And if it is, why? I don't get it. Huh? Let's take 11. I should find 178 blah blah blah. No, what are we doing wrong? Ah, subject number. We're squaring the number, but maybe the subject number, yeah, is the original number. No, that makes no sense. Ah, whoa, where did this value 1 come from? I completely read over it. So, yeah, we have not mentioned anything about a subject number yet in the code. No, we have not. Transform the subject number. To transform a subject number, start with the value 1. Set the value of itself multiplied by the subject number. Set the value to the remainder. Wait, so subject number starts with 1. How does the subject number change? We're transforming the subject number. Okay, getting confused. So we're transforming a subject number and we start with something called the value 1. And then we do the value multiplied by the subject number. Okay, let's take this terminology into our code as well. Yeah, so shared secret can go out of the window. Is this still something we do? Yeah. So this is the initial subject number. But instead of doing this, it's not nearly correct. So we have a value and a subject number. Let's make that a tuple. There's the original value multiplied by the subject number and the val modulus. Okay, so it's almost what we had, except totally not. This is more like it. So it's simple enough to not have a local variable in here. Value times the subject number and then remainder after dividing by this magic number. Okay. Value always starts at 1, right? Set the value. And what does this return? So we calculate a new value, which is what we just did. subject number stays the same. Probably subject number stays the same. So here we do value always starts at 1. Value starts at 1. And we provide the subject number. Value is not a function. Oh, it's a tuple. Let's get rid of the tuple. Did not make much sense if we only have to return a new value. So we calculate the next value and we recurse. And we keep using the 7 as a subject number, so that does not change. Let's see how far this takes us. 178 something something something. Yeah, and the 7th or the 8th one would be 576. 1, 2, 3, 4, 5, 6, 7, 8. Okay, we're there. So we can, if we know the public key, we can find the loop size. Yes, we should. So naively, continuing our naive strategy, we figure out this 11 and this 8. So given a, I'm mixing underscore and a and chemical. Let's do it underscore today. Given a public key. So we find the first one in we find the first, or we find the index of public key in the entire list. So this will work for the small example, probably. So let's try to find the loop size for this number. Solve by 1. Interesting. Oh yeah, index is 0 based. So let's put some parentheses around it. There we go. 8 and 11. So the naive approach has taken us to this point. So we can figure out the loop sizes. And if we have the other's public key, we can also figure out the encryption key by transforming it again. Yes, figure out one of the two party loop sizes, and then we actually need to do this algorithm again. Yeah, let's first see if it works. Let's take the card as an example, with a loop size of 8. Oh, that was this. Card loop size. What is it? Example 0? Yeah, let's use the if we figure out the card's loop size, we can take the door public key, and now we have to apply that algorithm, but we know how many times we have to use it. So the initial subject number is not what we're using here. Let's call this encrypted. Yeah, actually, this is what we need, right? let's extract that function, or let's make it accessible in a broader scope. And actually we don't need to, I don't know, actually, let's just duplicate it. So we need to know how many times we apply next. Subject number and loop size. If loop size is nothing, we're done. Otherwise, encrypt the next value subject number. Value starts at 1 and it's subject number. So yes, this is recursive, you are correct. Loop size -1, yeah. So this will just recurse until we perform the necessary amount of iterations. So we have the card loop size, and now let's encrypt the door public key given the card loop size. Yeah. That can be a long. $178. What? So this is the door's public key. Card's loop size is 8. I'm using next one. That's where it starts, but that's not a. Yeah. So let's do our trick again. We keep passing the value 1. We're not doing much interesting. Day 25. It's whoa. Null reference exception thrown by my IDE. That's promising. I have a lot of confidence in you now. So yeah, now we're threading through the value. That will work better. This will work wonders. Subject number and loop size. Actually, subject number does not change. Wow, why was that a problem? I don't know. Still weirdly not correct. We need to actually calculate the next value, which is what we're doing here. Nope. Yeah, this looks correct. What's happening? So we know card loop size is 8. That's correct. We provide this to encrypt, yeah. Door loop is this totally different number, yeah. If we encrypt it, it gives us the number itself. How? What? Oh, I can't believe. Why did I throw that away? If we're nesting functions and we reference the outer scope, yeah, that doesn't work. So it's value, subject number. What do we need to return actually? The value, not the subject number. So that was actually the problem. So this can go in theory. There we go. Oh, it's one of these days that I'm happy I have a day off, because I would not be very productive. Okay, so we after a lot of trial and error, misreading, skipping over very important numbers called 1, not understanding that we have 2 numbers to work with. We have like an algorithm down, but yeah, this probably will not really work for. I don't like this array thing. Yeah, but the input is an array. Let's keep it. Let's try it on the input. Doesn't matter which we take. No. So if one is really slow, we might try the other, or we might even run both in parallel until we find one. That would be an interesting way to try to crack it, actually. Yeah, because that's a big loop size. What is it? Let's see what the smallest loop size is. So this is actually the door. That's the door. Or in my head, at least. I don't think it really matters. It's just the one and the other. Yeah, you're right. It doesn't matter. It's never stated. So take the other number here. So this gives us the 302. Yes. And then this gives us the other number. Oh, that was way too fast. Oh no, there will be a part 2. Maybe work on the input, not on our example. Oh, jeez. It's really not my day, but okay. We have 40 seconds. So suppose we have to do this. Let's keep this in a buffer somewhere. Suppose we have to do this way more. What can we improve? There's probably a mathematical trick. Or no, there shouldn't be, because this is actual encryption. Rainbow tables? No. The only thing I can think of is don't use infinite recursion and sequences to figure out the loop size, because that is not the fastest approach to doing things. So we can get rid of that, but otherwise, I don't know. We would have to take a look at the actual numbers. So that was functionally correct, at least. It's that's one thing. I'll take it. Let's see what part 2 has in store for us. Oh, story time. So the door unlocks. We finally made it, everyone. We made it. What is a soft serve? Is it the ice cream? Oh yeah, it's the ice cream. I don't like it. I had it once. I had salmonella, like a serious disease, for a week. So no, no soft serve for me. So okay, soft serve in the basement failed. We're the only one that knows how to fix it. Why? Okay, so we get a reindeer taxi to go fix the soft serve machine. Yo, the resort 50 stars, yes. pay the deposit. Oh, this was it. We actually did it. Congratulations, we finished every puzzle in Advent of Code 2020. I hope you had as much fun solving them as I had making them for you. We very much did, Eric. Thank you very much for this year's puzzles. Yeah, contact details if you'd like to see more things. Yo. Follow him on Twitter. I do suggest to follow Eric on Twitter. He shares a lot of background information on Advent of Code. He does conference talks explaining like the performance issues he has, because can we see how popular Advent of Code has gotten? There's this yearly, no, it's actually the second year, only the second year that I managed to like run through the entire calendar. There is this one. It shows you how many people are participating. Ooh, spoiler alert. Ooh. I love it. Oh, even the sea monster is moving. Diffie-Hellman. So it was not really RSA, it was Diffie-Hellman encryption. Let's go look that up. No, it's a spoiler. Let's not. We finished. Why would it be a spoiler? Key exchange, yeah. Is it literally what we've been doing? It's literally what we've been doing. Cool. Oh, cool. Every puzzle had Easter eggs, and if you finish them, you will they get highlighted. Hover your mouse. I will be going through them. I won't be going through them on stream. I will leave these surprises for you to find out. So yeah, this was Advent of Code in F#. Eric Wassel is a great guy. Make sure to go look him up. I hope you will enjoy the coming periods. If you have holidays or vacation periods, take care of yourself, take care of your friends, and I will see you next year. Bye.